Well, uh, welcome everyone to the second day of the Congress. Today we start up with Arturo Pianzola from Universidad KS in Buenos Aires and University of Alberta in Canada. And he will be talking about fiber-wise criteria for forms of algebras.
Thank you, Federico. I want to sincerely thank the organizers. Fernando Kuckerman is a person and a mathematician that I hold in great respect and I admire a lot. So it's just wonderful to be able to be part of this event. So I want to start with a question of Bourbon. So, and then I'm going to describe a framework which is really based on FGA3. So the Mazur and Grothendieck study of reductive group schemes. And then I'm going to use that to answer this question. So the question there are many things that you won't get at the beginning, but I will try. So G over C is a finite dimensional, simple Lie algebra. And then you have the ring R of Laurent polynomials in C. And what Bourbon and his students were doing is they were trying to understand solution of the Yang-Baxter equation using affine Kac-Moody Lie algebras. And they had to know the following. So they had a Lie algebra L prime over R. And what they knew was that L prime is projective of finite type. I'm going to abbreviate as an R module. And then the second thing that they knew was that if they took L prime and they factor out T minus Z, where Z is a non-zero complex number, then what they got was G. And the question that they had to know is L prime a loop algebra? Now, of course, you don't know what a loop algebra is, but I will tell you. But it is related to affine Kac-Moody algebras, which is a nice class of Lie algebras that have appeared in string theory, in the Langlands program. And the answer is yes. And the proof, as we will see, is all you have to do is you have to show that there exists some FPPF, so a ring extension which is finally presented and faithfully flat, such that when you go to R prime from L, what you get is essentially G. And for reasons that will become apparent later, I'm going to rewrite this way. OK. So it's a problem in Lie theory, but this is a conference in algebraic geometry, or partly. So I'm going to try to answer this using algebraic geometry. So first of all, this thing in here for us should be rewritten by saying that the fiber So the residue field of this ideal is C, and you're just saying that the fiber is G. Okay, so what are the loop algebras? So what you do is you take an automorphism of G, which is of order, it's a finite order. It doesn't really matter. So then your Lie algebra splits into eigenspaces. So G, J are the things with sigma of x. You fix a primitive root of unity. You take a ring which is a very nice extension of R. So you just look at some nth root of t on some algebraic closure of the function field on t. And you do the following. So the loop algebra, which is denoted by LG sigma, what it is it sits inside this huge infinite dimensional Lie algebra. And what it is G0 you pair with R, and G1 you pair with T1 over N R. So essentially what it is the sum, direct sum, of G0 tensor T J over N R, where J goes between 0 and N minus 1. Let me make an observation. So this is, maybe I'll come back to that observation in a second. So why are these things of any interest? Well, so can I erase that? Okay. Maybe I'll keep the G. It's a nice G. So why would anyone care about this? Well, so let's go on a review of classical theory of split or complex finite dimensional Lie algebra, simple. So you know they're given by a Cartan matrix. So let's do a column here of A and B. So you could have 1, 1, 1, 2, 1, 3. Then I'm going to put, I don't know, 5. I like 24. 2, 2, 1, minus 4. So what the Kac-Moody algebras are is they are given by, so these are Cartan matrices. These are not, but they're given by generators and relations. So this is very nice, but it doesn't give you any clue as to what the Lie algebras look like. So for example, if I were to tell you, okay, this is a Lie algebra with 6 generators and all these relations, you're going to say, okay, you're totally crazy. I mean, this is 3 by 3 matrices of trace 0. And this is SO5. And this is G2. But you wouldn't think of G2, you would think of the derivations of the octonion. It has a very concrete picture. This we have no idea. It's a Lie algebra, but this, however, is really interesting. This is nothing but SL2 tensor R. So really what it is the loop algebra of SL2 based on the identity. This is even more interesting. So you take SL3, So the thinking diagram is like that, and you have, so what is the automorphism group of G? Is the connected component is PGL3, and then you have a group of order 2. There is an outer part which is generated by that guy that essentially is taking a matrix X to minus X transpose. That is not given by conjugation. And then what this Lie algebra is the loop algebra of SL3 based on that sigma. So the loop algebras give you, is something that Cox and Moody prove independently, gives you realizations. They give you a very concrete picture of what this important class of Lie algebras actually look like. So really what Bergman is asking is this guy an affine Cox-Moody Lie algebra? Now, it's very easy to see. It's linear algebra, but the best way to do it is using Galois theory. So R prime is actually a Galois extension of R. So it's FPPF in spades. And it's very easy to see that if you take LG sigma, by the way, very important observation, the one that I tell you I was going to come back to it. This is not a Lie algebra over R prime. When you multiply something in here by t by 1 over n, you go outside it. But if you multiply by a full power of t, which is t 1 over n raised to the n, because the ith eigenspace and the jth and the jth plus n eigenspace are the same, you stay inside here. So this actually is infinite dimensional Lie algebra. It's a Lie algebra over R. As an Lie algebra over R actually is a free module of rank the dimension of this. So it's a really nice finite dimensional object over a ring. So when you do the base change, what you get is this. So what you have is two objects over R that locally, in this case for the final étale topology, but locally they look the same. So this assertion then, so what we know is that these algebras are forms. So this is what is called a twisted form. Something that locally for these Grothendieck topologies look the same. So we know that the things he's looking for are forms. So why is this enough to prove this? Well, because I proved in 2005, I proved a little result that says that if you have an arbitrary reductive group scheme, this H1 vanishes. So if you know things about torsors, you will see that, so this fits inside, you see, you have the adjoint group, you have the outer part. The outer part, the H1, is going to give you the loop algebras. But you could have lots of things that come from the inner forms. And it's not just enough this guy. You have to twist this guy, and then you get a group that doesn't exist over the complex numbers. And all those H1 vanishes, so what you get is just the loop algebras. So, because of that result, we know that all the forms are loop algebras. So what we have to show is that this L prime is actually a form of G tensor R. That's it. And we're going to do that using algebraic geometry.
Sorry, your result that you mentioned, you proved this H1RG. What is G?
G is, that's right. So what happens is you get this sequence. And by the way, this is a variation. there is this Serre's conjecture 1, which was proved by Steinberg about the vanishing of H1 for groups, algebraic groups over certain fields. And this is a variation of that for this particular Dedekind ring.
Also, it's true only for R.
No. It's true for, well, certainly it's false in general. But it's true for that particular R, okay? And for other, but in general, it's totally false. I mean, if the Picard group of R is not 0, H1 of a torus is not trivial. So, but anyway, so you have this. By Grothendieck, so the fundamental group of R is just the completion of Z. So all you get is just the conjugacy classes of diagram automorphisms. Okay, so let's look at this particular case. So here you have 2 elements. And you want to know what gets mapped here. And this classifies all the forms. That's sort of the Zen of torsors approach of G tensor R. So what goes anywhere, so this is the interesting case because it's easy to see that H1 of PGL3 is trivial. But to see what goes to the other guy, you would have to twist that by H, by E, by the torsor E. And this group is a group scheme over R, which does not come from the complex numbers, it's not split, and it's actually a quasi-split group. It's a form of PGL3 that becomes PGL3 when you go to R prime, but it has, for example, a one-dimensional, torus are two-dimensional, but the diagonal part is just one-dimensional, and the root system is of type BC1. So it's non-reduced. Okay. Good. So I hope, I know the audience is not in Lie theory, but I hope I was able to tell you about an interesting question on infinite dimensional Lie theory that we will try to solve using algebraic geometry. So the main characters here, which is we have a scheme X, and we have a group scheme over X, which we assume is a finite presentation. And there is really, I mean, we have to come back to that case anyways. There is, I will alternate between, but there is no really much harm in assuming that you are in the affine case. So that's a Hopf algebra. And I have to introduce a few characters that characters as in a play, not characters of a group. Anyways, so the first thing I want to do is I want to talk about the Lie algebra of Lie. Well, the two. So this guy is actually a sheaf on the algebras, but so he takes a ring. So here S is a ring extension of R. By the way, this R is not that R. Now R is an arbitrary ring, okay? And S is an arbitrary ring extension of, I mean, we'll prove something much more general than what we need for Berman's answer. So you evaluate the dual numbers. You send epsilon to 0, and watch, this is the kernel of this map. And so you see, you have RG, you have the co-unit or the unit section in general. So you can view S as an RG module that way. And what this guy is just the derivations of RG in S. When you view S as an RG module this way. And this is the same thing than home omega 1 S. And this omega 1 is just the Kähler differentials of Rg over R, where you do base change with a unit section. So this is always affine, because this is also home of algebras, of the symmetric algebra of omega 1 on S. So it's affine, and it's usually denoted by V omega 1. This is an affine scheme. But at the end of the day, we want a Lie algebra, and the Lie algebra appears by taking Lie of G and evaluating at R. So this is nothing but the dual of omega 1. And if omega 1 is projective of finite type, or locally free of finite rank in the non-affine case, then the two things are related very well. So Lie G of S is, and this is simply because of this and the fact that omega 1 is isomorphic to the double dual, because it's projective of finite type. Okay. Because to do things, we're going to need this guy, but at the end of the day, we need the real Lie algebra for this question. Then I want to say something about G0. So this is in, so you know, if you don't, so HGA3 is a huge thing. It has 24 exposés, and this is in exposé 6b. And so it's defining the connected component of a group scheme like this. And the idea is the following. So you define a functor first. And so let me just, I'll tell you what it means. So what I mean is the following. So this guy is a morphism like that, and then you do base change. So P is in X, but so this is an algebraic group over the residue field kappa P. So you have a concept of the connected component. So what you ask is that it goes like that, okay? So at this point, this is just a group functor. Let's say G is reductive. So that means it's smooth, it's affine, and when you look at all the fibers, or geometric fibers, so you see why this fits into the language of HGA3. What you get is a connected reductive group scheme in the traditional sense, whether it's Borel or. So if you take a point in your base, so this is, say, a prime ideal of R, then you have the type of G at P, which is a type of GP. So let's say, for example, in this case, this crazy group that we looked about, okay? So that, of course, this is not reductive because it's not connected. But that part is, this twisted group is actually semi-simple. So, for example, you could say that's a group of adjoint type and of type A2. And so I think I forgot, but I think it's 19. But anyway, the type is locally constant. So if X is connected, for example, the group will have the same type at all points. And the last thing I have to tell you about
you mean, you're not meaning that whether it's split or not?
Absolutely, it's not split. But what it means is when you go to the algebraic closure, so the geometric fiber, then you do get a split reductive group. And it's given by a root data. So it's a root system, which will be, say, type A2. But then you could have, it could be SL3. So it could be simply connected, adjoint, things in between. Yeah? So maybe in another fiber, it will be split. But when you go to the closure, it's, so let X0 be the close points of X. So X is Jacobson if X0 is not dense, it's very dense in X. So this is, I'm very happy I could do something with Jacobson things, because Jacobson was the supervisor of the supervisor of my supervisor. And but anyway, this is all in EGA4. I mean, Jacobson rings is a known thing, but Grothendieck did it for schemes. But what very dense means is that if this is closed, and you look at that intersection, so essentially it's dense on every closed set. Okay, so now we prove the main theorem. So let's assume that X is integral. So by the way, that's a Jacobson ring, so we're in good shape. And Jacobson. And let's assume that the GQs, so the fibers, are smooth of all of the same dimension D for all Q in X0. Then all the fibers are smooth of dimension D. And then this functor G0 that we're talking about actually is, because G0 in general is just a group functor, but this actually is a scheme. It's an open subscheme. So let me sketch the proof. So this is a huge result. So this is again in, so that 1 implies 2. This is X possess 6p. So how does the proof of one, so it's an open smooth. So if you're observing, we're not saying that G is smooth. This is very mysterious, okay? So the idea is the following. So we use Chevalley. We're going to use Chevalley many times. So there exists U, in fact, affine, but it doesn't matter, dense. So that the restriction is flat. So this is a generic flatness, and all the fibers have the same dimension. Okay, so what you get out of this is, so if you take, so when you get into the Jacobson world, it's very hard to get out. So any open of a Jacobson is Jacobson. This is a finite represented object over a Jacobson, so it's also Jacobson. So all these guys are Jacobson schemes. So if you take a Q0 in G U0, then is flat, and the fiber is smooth. So is smooth at Q0. So the fiber would be, you apply F to Q0, you get a point on Q that is in U0, so you get that fiber there. So it's smooth on a neighborhood of Q0. Okay? So now you take the union of all those neighborhoods. And of course, X0 is dense, but that's not enough. You need very dense, because you see, when you take this union of all these neighborhoods, you get an open set. But you don't know it's all of U. But suppose it's not all of U. So the complement is close. But X0 intersects. If the complement is not empty, this intersection cannot be empty. So there is a point, but it's not supposed to be there because you took all the neighborhood. So you get that it is smooth. So now we use Chevalley again. So smooth, what is called of relative dimension. So the fibers are all equal dimensional. So this is the upper semi-continuity. So let's say that we take a point in X. And let's look at the dimension of the fiber. Let's call it C. So then you define FC to be the points in your scheme where the dimension of the fiber is larger or equal than C. This, of course, is a non-empty set because it contains P. And what Chevalley tells you that this is closed. Okay, but then FC intersects X0. And all the guys in X0 have dimension D. So what this tells you all these guys have the same dimension. So. Good. So we haven't used that part, but we will now. So now you take the generic point we're assuming the scheme is integral. Well, then P belongs to the closure of the generic point. But the generic point also belongs to F eta, because it's of dimension, the dimension of the fiber. But this is closed. So this is inside there. But eta is in U. Eta is in any non-empty open set. So that means that the dimension of GP is actually exactly D. Okay? So now what you do is you prove, so the omega 1 is of finite presentation. And then what you do is you prove an analog of this for the Lie algebras. And what you get, so these are, of course, Lie algebras over different fields. Now, you know that the group always has dimension which is less or equal. But these groups are all smooth. So by the smoothness criteria, the Lie algebra and the group have the same dimension. But then this was also D. So that tells you that the Lie algebra of this group is the same dimension as the group, so the group is smooth. So that's the proof of that. And once you have that, you can get that condition. Okay. So now, we'll try to prove so by one now I mean this. So let's say that X is integral, is Jacobson, But we need something more, because, I mean, Lie algebras in positive characteristic are really bad, and of characteristic 0. So in the affine case, it will mean that R is a Q vector space. So we have a simple Lie algebra. So we have a type, and we let G over X be a split adjoint. So in the original example, it will be, say, PGL3, split PGL3. Okay, well then, the Lie algebra of G is, let me call it G. This is not the eigenspace. I'm just calling this G0, where this G0 is over Q is split finite dimensional simple. Okay. So in this situation, and now we take so it will be a sheaf of Lie algebras in general, but let's take Lie algebra over R, and let's assume that L prime is a projective of finite type. So the condition that, and second, that L prime Q is a twisted form of LQ for all Q in the closed points. So what does this mean? Of course, twisted form will mean that locally FPPF, these things become the same. Okay? But you're in a very nice world here. I mean, this is an automorphism of the Lie algebra, is an algebraic group over a field. So it's smooth because you're in characteristic 0. So in fact, you have a point over the separable closure. So any torsor will vanish there. So really what you're saying, this is the same thing than saying that when you go to the algebraic closure of your residue field, what you get. So they become the same when you go to the algebraic to separable closure. But this, of course, is this guy. Which is semi-simple. Then L prime is a twisted form of L. And that's, so we not only we have this condition in here, but in this case, actually, the algebras are the same. There is not, you don't even need to take twisted forms.
Sorry, who's L?
Sorry?
Who's L?
L is, thank you. The Lie algebra of the split guy.
So R is still C?
No, at this case, I'm still in the general case, okay? But so now that's a good point, because if we can prove this, then we have, so you see, in the introduction when I was talking about loop algebras, I mentioned that these are twisted forms. So and we have to show, it was enough to show that it's a twisted form, and that's what we're doing. So a corollary is Berberman. Because you take R to be this guy, and you take G to be this Lie algebra. So you get it as a particular case of we're going to prove. And how do you prove this? So I said I was going to take 55 minutes. So, but the idea is the following. So I won't bother you with the details. But so let's say that H is odd L prime. So what does this mean? So this is a scheme. So you look at that S Lie algebra. It's a group scheme, and then you look at the automorphisms of that Lie algebra. Okay. So what do we know about HQ bar? Well, this is the automorphism of L prime Q bar, which is the automorphism of LQ. And the automorphism of LQ, as I said, is the adjoint guy, and there is some finite état group here, which are just the constant group corresponding to the symmetries of the Dynkin diagram. So you're in characteristic 0. So these are all smooth, and they are all of the same dimension. The dimension is the dimension of G, which is the dimension of the Lie algebra. So okay, so the theorem that we just proved tells you that the connected component of this guy is smooth of relative dimension D. But if you look at H0Q, what you get is, well, you're just taking connected component here. So what you get is a twisted form of G. So when you go to Q bar, you actually get G at Q bar. So there is a result in Exposé 22. So this uses that this guy actually is affine or finite presentation. That will tell you that H0Q is reductive on a neighborhood of Q. And because X is Jacobson, that will tell you that actually H0 is reductive. Okay, what is the type? Well, we're assuming that the thing is integral, so it's connected. So the type is the same. So you have two reductive groups of the same type. SGA3, Exposé 23, tells you that they are twisted forms of each other. It's a twisted form of G. So it becomes G after some FPPF extension. Well, let's see if we can now compute Lie of G prime. So what is Lie of G prime? Well, it's Lie of, oh, so by the way, what is G prime? So I'm going to call G prime this group. Okay? So Lie of G prime is Lie of H0. The Lie algebra doesn't see it only sees the connector component. And this is the automorphism scheme of L prime. And this is well known what this is. This Lie algebra, this is an actual Lie algebra or sheaf of Lie algebras, is the derivations of L prime. Now, by the way, H0 is a twisted form of G, implies that, and this is what we're calling G prime, it implies that the Lie algebra of G prime is a twisted form of the Lie algebra of G, which is L. And this Lie algebra is that. Now, this is a smooth group, so this is projective of finite type. And you see, the problem is we don't know that this is L prime. If we knew that this was L prime, we're done, because we want to show that L prime is a twisted form of L. But we know that it's that guy. And you have the adjoint representation, and I'm essentially done, so don't. And now the key assumption, that L prime, by assumption, is also projective for finite type. So what happens when you go to all the fibers? Well, this is against Chevalley. So now when you go to the fibers, you have a semi-simple Lie algebra over a field of characteristic 0. And Chevalley tells you that every derivation is inner. So you can use Nakayama then to conclude that AD is an isomorphism. So you get what you wanted. So this is L prime, and we knew that this guy, Lie G prime, was a form of L. So that's the end of the proof and the end of my talk. Thank you very much. Yeah. Good.
Thank you. Comments, questions? No? Well, I have a question.
Sure, yeah.
What remains of the original R in the proof is very little.
Yeah.
It's just the Jacobson,
Well,
pretty much the Jacobson.
For rings, Jacobson just means that any prime ideal is an intersection of maximal ideals, which for this case, for this ring is...
Even the definition of a loop algebra just uses some forms of hypothesis on the fundamental group of R.
To conclude that there are very few of them, yes, yes.
So could you produce more loop algebras in this fashion?
Yes,
using other rings?
Yes, we created something called loop torsors, and they are connected to what you would call multi-loop algebras. But what is amusing is that there are people in number theory actually using these loop torsors, and this is defined as you said. Essentially, you can define loop torsors for so the role of R is played by any scheme X over K. And you look at, so you have now a group G over K, and you look at torsors of X under G, and essentially you're asking that they come from the fundamental group. So they're that's why we call them loop torsors, yeah.
Thank you.
Okay.
Any more questions?
Yes?
Just in your, when you say form, so it's the standard question, do you always need FPPF or you can reset it out?
That's a really good point. In characteristic 0, you can get away with a tull, but in the main result that in the main result, we're not assuming characteristic 0, so you need FPPF, but even right away for No, okay, so there were two parts. So on part 2, we prove that if you have all the fibers at the close point were smooth, and that did not assume characteristic 0, yes. But we did not talk about torsors in that case. But you are correct. In this case, the torsor will be locally trivial et al. Absolutely. Because the underlying structure group is smooth. Yeah. So if there are no questions, I just wanted to, it's not a question, I wanted to say something. So when, this is this thing about this vanishing of H1 and loop algebras and stuff like that, it was the first talk that I gave at Fernando's seminar, and it was in 2007. And through that seminar, I met all of his students. I also have a chance to talk to him a lot. Some of those students and students of their students are people that I'm very close to. People that were not his students are also people that I'm very close to that I met at the seminar. I've written papers with some of them. So it's been for me an incredible experience to be part of the Fernando seminar. And it's funny because someone yesterday mentioned that Fernando will take them for a walk. And the first time that, before I was given the talk in the seminar, he actually took me for a walk. And you know that SGA3, it's the seminar is called Bois Marie, so it's Mary's Forest, and we were walking through Bosque de la Costanera. So for me, Fernando's seminars, I always refer to it to Seminario Bosque de la Costanera. Yes, I know. Okay, thank you again. Thank you.